Swayam Prabha. Digital India. Educated India.
Let me discuss today fundamentals of converter steel making technology. I have said while discussing converter steel making practice, I said over there that typically liquid steel is tapped in every around 60 minutes irrespective of converter capacity. Now, it is always a curiosity how this happens. So, I have thought about it, and it is the availability of oxygen, it is the availability of oxygen for refining of hot metal, for refining of hot metal is probably the main cause of very small tape to tape time of the order of 60 minutes, and this tape to tape time does not depend upon the converter capacity, whether a converter is 50 tons or a converter is 400 tons. The tape to tape time is approximately of the order of 60 minutes. This depends upon the availability of oxygen supply, and at the end of the lecture you see whether it depends on available of oxygen supply or not. So, the availability of oxygen, let us see how oxygen is available in converter steel making. So, availability of oxygen. Availability of oxygen. Oxygen during the refining of hot metal in converter is available energetically. This energetic supply of oxygen is obtained by passing a certain flow rate of the oxygen through the nozzle. That is, whenever a certain amount of gas passes through a nozzle, an energetic form of gas supply is achieved. Now, there are two different types of nozzles. One, I will draw it for you. So, this is a sort of convergent nozzle. This is a convergent nozzle. This is the direction of flow, for example, of oxygen. This a minimum cross sectional area, this is called throat of the nozzle, throat of the nozzle. So, this convergent nozzle is characterized by decrease in the flow cross sectional area as the flow proceeds, and the cross sectional area attains minimum, which is called throat of the nozzle. Another type of nozzle is a convergent divergent nozzle, which has been sketched over here. This is the convergent portion and this is the divergent portion. So, this particular portion is convergent portion and this particular portion is divergent portion. This is again the direction of flow of oxygen. That means, the cross sectional area of the flow passage decreases first, attains a minimum value which is called throat of the convergent divergent nozzle, and after attaining the minimum cross sectional area, the cross sectional area further increases in the direction of the flow, and these nozzles, they are called convergent divergent nozzle, or they are also called Laval nozzle. And these nozzles are characterized by, say, this is the D exit, that is the exit diameter of the nozzle. This diameter is D throat, that is diameter of the throat, where a minimum cross sectional area is attained. Velocity of jet, it can be expressed in terms of Mach number. What is the Mach number? Say Mach number is velocity of gas upon velocity of sound, that is V upon A. Now, A can be calculated by kappa r T0, where kappa is the isentropic exponent of the gas, and its value for all diatomic gases is equal to 1.4. R is gas constant, that is universal constant divided by molecular weight of the gas. T0 is the temperature. Now, suppose if I want to calculate the velocity of sound of oxygen at temperature 298 Kelvin, then A, that will be equal to 1.4 into 8314 divided by 32 into 298. So, A comes out to be equal to 329 meter per second. That means, this is the velocity of sound. So, thus m is equal to 1. That means, gas exits the nozzle, at sonic velocity. M less than 1, gas exits the nozzle at velocities smaller than velocity of sound. And m greater than 1, gas exits the nozzle at velocity greater than the velocity of sound. So, convergent nozzle can accelerate gas from some velocity to maximum up to m less than or equal to 1. So, these type of nozzles are called subsonic when m is less than 1, and sonic when m is equal to 1. So, such nozzles are called subsonic to sonic nozzle, depending on the value of Mach number at the exit of the nozzle, whereas convergent divergent nozzle can accelerate the gas to any value where m is greater than 1. So, these nozzles are called Laval nozzle as well as supersonic nozzles, The acceleration of gas to any value of m greater than 1 is achieved by appropriate design of the nozzle through maintaining a ratio of d exit to d throat, which is a function of stagnation pressure of oxygen supply. In converter steel making, Laval nozzles are used. As such, in our lecture, we will be concentrated on Laval nozzle. Gas velocity at the exit of the nozzle, it corresponds to m equal to 2 to 2.4 in almost all converter steel making operation. Flow rate of oxygen is of the order of 3 normal meter cube per minute per ton, which converts to 660 normal meter cube per minute for a 220 ton converter. The pressures of oxygen supply, it varies between 10 to 14 bar. In all converter steel making, multi nozzles are used. The said amount of oxygen is supplied through 3 to 6 nozzles, and the number of nozzles, it depends upon the capacity of the converter. Let us see first of all the behavior of gas when it exits a single nozzle. Now, a gas exiting the nozzle spreads in the surrounding and is called a free gas jet, as shown in this particular figure. So, this is a free gas jet, produced by a supersonic nozzle. So, this portion is the free gas jet. You see that the jet begins to spread as the gas exits the nozzle. Now, this particular portion is the Laval nozzle. This is the direction of flow of, for example, oxygen. Now, as the gas exits the nozzle, it spreads into the surrounding because of the entrainment of the surrounding. So, surrounding is entrained this way, this is the entrainment of surrounding. What will happen due to entrainment of surrounding? The gas velocity will decrease as the gas moves downstream the nozzle. Why it will decrease? Because jet will spread. So, if I show, this is the direction z, which is the axial distance, and this direction is r, which is the radial distance. So, you note from here or from this particular diagram, as the gas exits the nozzle, you note that the jet begins to spread. That means, as the jet moves downstream the nozzle, the radial spreading of the jet begins. But a supersonic nozzle is characterized by delay in the radial spreading of the jet up to a certain length downstream the nozzle. So, I say this is the upstream of the nozzle, this is the downstream of the nozzle. This is, if I say LP, this LP is the potential core or length of potential core. That means, in this portion of the length, the velocity of the jet radially and axially is same as that of velocity at the exit of the nozzle. That means, jet does not spread in this particular region, and this length may be of the order of 6 to 7 times the diameter of the exit of the nozzle. However, it depends upon the pressure also. Now, the jet begins to spread beyond the length of the potential core. So, this particular length, in fact, from here to here, this is LS is the supersonic core, is the supersonic core, or you can call also that from here to here the length of the supersonic core beyond the potential core. The M of the jet is equal to 1. Beyond M is equal to 1 region, that is the subsonic region, that is subsonic region downstream the nozzle. Due to entrainment of surrounding, number 1, radial spreading of jet. Number 1, radial spreading of jet. As a result, mass of the jet at any point downstream the nozzle will increase. Why? Because of entrainment of the surrounding. So, as we move downstream axial distance more and more, mass of the jet will be more and more. Second point, this is what is happening. The radial and axial velocity decreases. That means, if I note here point Z1 and point Z2, then velocity at point Z1 downstream the nozzle is greater than velocity downstream the nozzle at Z2. So, you must note very carefully from here these two important things. One is the radial spreading of the jet, and the radial spreading occurs because of entrainment of the surrounding. As a result of entrainment of the surrounding, the main part of the jet, if it consists of oxygen, it gets diluted, number 1. Number 2, the radial and axial velocity, they decay as we move downstream the nozzle. So, this is in short the behavior of gas jet when a gas discharges into the surrounding. Now, in the converter steel making, multi nozzles are used. The behavior of multi nozzle jets, that depends upon number of nozzles and inclination angle of each nozzle with the axis of the lance. That means, if I take the flow rate of the gas constant, I allow the gas to flow through a single nozzle and I allow the gas to flow through multi nozzle, then the jet produced by single nozzle will be somewhat harder as compared to that produced by the multi hole nozzles. This is the angle of inclination. Alpha is the angle of inclination. Alpha is the angle of inclination of each nozzle with the axis of the lance. This is the lance, this is the axis of the lance, and alpha is the angle of inclination. Now, this angle of inclination will decide whether the jet produced by independent nozzle will coalesce downstream the nozzle or will not coalesce downstream the nozzle. So, multi-hole nozzle, they divide the flow rate such that n into a n, that is equal to A, where n is the number of nozzle, A n is the cross sectional area of each nozzle, cross sectional area of each nozzle, and A is the area of a corresponding single nozzle. So, if you put it pi by 4 d square, then we get d, that is equal to root n into dn. For multi-hole nozzle, the coalescence of jet will depend upon the angle of inclination of each nozzle. So, in this figure I have shown that how the angle of inclination affects the jet coalescence. In this particular figure, the flow rate of oxygen is coming in this direction, and this is the blue one is the jet produced by one nozzle, and red one is jet produced by another nozzle, So, you can see how both the jets are coalescing just downstream the nozzle. Now, if I increase the angle, then obviously the jet coalescence will be delayed, and jet, no doubt jet will coalesce also, but they will coalesce after a very long downstream distance. In this figure, what I have done, I have taken alpha such that the jet issued from each nozzle, they coalesce at a higher distance downstream the nozzle. So, this coalescence and non-coalescence of the jet is a very important part of the converter steel making. So, this particular thing is an example of non-coalescence of the jet, non-coalescing jet. Why it is important? A coalescence jet is very similar to that of single jet. A single jet produces a single jet. If you have 4 nozzles, 4 independent jets, if the angle of inclination is very small, for example 3 degree or 4 degree, then they will coalesce just downstream the nozzle. So, the effect is that of a single one. If I increase the angle of inclination, then I may get 4 independent jets, and on account of that I am rather hitting a larger surface area as compared to that of a single jet. But the non-coalescence will depend upon the angle of inclination. No doubt if I increase the angle of inclination, then the jet will non-coalesce, but then increasing the angle of inclination will also affect that the jet may hit the side wall. So, one is to take a compromise between what angle should be there and what angle should not be there. Normally, say alpha is 10 to 12 degree for 3 hole, I will just write down alpha equals to 10 to 12 degree for n equals to 3 and 4 number of nozzle. For n is equal to 5, alpha is of the order of 15 to 16 degree. From refining point of view, the behavior of jet is important. Behavior of the jet, it depends on the surrounding of the converter. In the converter, as I have said, the blow begins and the oxygen jet is surrounded by the hot atmosphere. So, the surrounding is different. As the blow continues, the surrounding of the jet changes. It starts with the brown fume, then taken over by the red fume, and then taken over by the carbon monoxide flame. So, the surrounding is also changing as the blow progresses. Some 25 to 30% of the blow has proceeded, then the surrounding further changes, then the jet may submerge into the slag. So, the surrounding has become now a slag which is loaded with gas bubble and droplets of metal. So, what I mean to say is that surrounding in the converter is changing from start of the blow to end of the blow. So, in such a situation, it is important to know how the jet behavior depends upon. So, in fact, the jet behavior it depends upon the density ratio of, that means density of surrounding upon density of jet. A ratio equal to 1, the density of jet is that of surrounding. So, it is with that reference I am now comparing a ratio when it is less than 1 or when it is greater than 1. So, if the ratio, that is if rho surrounding upon rho jet is less than 1, that is rho j is greater than rho surrounding, then jet is denser than the surrounding, spreading of the jet will be very slow. How slow? It will depend upon what is the value of the ratio rho surrounding by rho jet, that is how decrease it is less than 1. In this particular case, length of the potential core, length of the supersonic core will be longer as compared to when the ratio is equal to 1. If this ratio, say rho surrounding upon rho jet is greater than 1, that means jet is lighter than the surrounding, jet spreads faster as compared to that of the surrounding when the ratio is equal to 1. The faster spreading of the jet will decrease the length of supersonic core as well as length of potential core. In converter steel making, that the surrounding is continuously changing. So, that point is to be considered, and on account of the change in the surrounding, it is very difficult to calculate the velocity of the jet at any point of time, because for calculation of the velocity of the jet you must know the ratio of density of surrounding upon density of jet. If that ratio is uncertain, then it will be difficult to say what is the velocity at which the bath is hit at the time of the blow, that is action of free oxygen jet. Now, as I said, it is difficult to find out the velocity, but you know that mass of the jet increases downstream the distance, velocity of the jet decreases. So, the momentum of the jet, that is m into v, is conserved downstream the nozzle. That means there is no, that means the momentum flow rate within the jet is constant, and that is a very important property. Now, we define a term which is called dimensionless momentum flow rate. Dimensionless momentum flow rate in order to define the action of jet at a particular distance, as that is equal to m dot upon rho L g into x cube, where m dot is the momentum flow rate, rho L is the density of the liquid in kilogram per meter cube, x is the distance. Now, for example, for 150 tons converter capacity, if x equal to 3, dimensionless momentum flow rate number can be calculated. M dot can be calculated, then this m dot, it comes out to be equal to 4057 Newton. Then if I calculate now the dimensionless flow rate number SI, that is equal to 4057 upon 7000 is the density of hot metal, into 9.81 into 27. So, this becomes equal to 2.19 into 10 to the power minus 3. If x I take equal to 1.5, where x is the launch distance, then this number psi that is equal to 0.0175. What this says? The value of the dimensionless momentum flow rate number increases as the launch distance decreases. That means, now we have got a parameter in hand which can describe the effect of oxygen free gas jet in terms of refining. Now, as I have said that it carries the momentum flow rate and so on. So, we can determine the momentum flow rate by the following equation. We can determine the momentum flow rate within the jet by the equation, that is m dot, that is equal to 1.029 into 10 to the power 5 P 0 into n into d star n square 1 minus P upon P 0 raised to the power 0.286, where n is the number of nozzle, dn is the throat diameter, P 0 is the pressure, supply pressure rather, and P is the atmospheric pressure. Now, this pressure P 0, it can be calculated by P 0 in bar, that will be equal to 6.755 T raised to the power 0.104, where T that is equal to capacity in tons. Throat diameter can also be calculated as a function of converter capacity and number of nozzles. Say T star n, that is throat diameter, that is equal to 7.46 upon root n into 10 to the power 3 T raised to the power 0.446. Now, as I have calculated earlier, now I have given you the equation. In illustration I can do it. If I take converter capacity as 150 tons, then P 0 comes out to be equal to 11.37 bars, and D star n that comes out to be equal to 0.035 meter. So, I can calculate now m dot, that will come out to be equal to 4057 newtons as the value I have used earlier. Now, depth of penetration of a jet which is hitting the bath can be determined. Say depth of penetration of a jet, hitting the bath vertically, it can be determined by an equation H in meter, that is equal to 4.407 into x into dimensionless momentum flow rate number raised to the power 0.66. So, if I take now H say is equal to 0.23 meter, x is equal to 3 meter, and psi is equal to 2.19 into 10 to the power minus 3. So, what I have done, I have calculated the value of H, which is equal to 0.23 meter for a distance 3 meter, and dimensionless flow rate number psi is 2.19 into 10 to the power minus 3. Now, if x is equal to 1.5 meter, earlier I have calculated this value was equal to 0.0175. So, this H that was equal to 0.46 meter. The first where H is equal to 0.23 meter is called a shallow penetration, and one with 0.46 meter, that is called a deep penetration of the jet. And this shallow and deep I have shown in this particular figure, where you note that this is a sort of a profile of a converter, this is the lance, this is the lance, this is the oxygen jet, so in one case the distance between the bath and the lance is greater in A, in B the distance between the bath and the lance is lower. So, if I increase the distance, then the penetration in the of the jet into the bath is shallow, whereas if I decrease the distance, the penetration of the jet in the bath is deep. So, in the terminology of refining, this particular practice is called soft blow. This particular practice is called soft blow, where this is called hard blow. This is called hard blow. So, what we note from here? That a jet or a free gas jet which is produced by the constant volume flow rate of the oxygen can be made soft or hard, or between the two extremes soft and hard, the jet can be made progressively harder and to end at the hard jet. Because how? If from the soft blow mode I progressively decrease the lance distance, then I am progressively increasing the depth of penetration and progressively I am making the jet harder. So, the characteristics of soft and hard jet are as follows. The characteristics of hard jet and soft jet are follows. This is the soft jet, this is the hard jet. For the soft jet, I have shallow penetration, here I have deep penetration. This is one important characteristic. Another important characteristic, the availability of gas is on surface or just below the surface, What is here? Gas is available deep, gas is available deep into the bath. That is one very important property of the hard jet. Third, jet velocity is low. Jet velocity is low, whereas the hard jet, jet velocity is high. Jet velocity is high, and as a consequence, the droplets are produced by the hard jet. So, for example, if the jet is chemically reactive, then what this soft jet and hard jet means? A chemically reactive jet means, again the jet has mass and velocity. So, mass of the jet will be consumed, or it will be distributed, or it will be diverted, and velocity of the jet will be used to create the mechanism for faster mass transfer reaction. So, in the light of soft and hard jet, what are the effects that it can induce into the bath? I write down here soft jet. A soft jet will promote oxidation of iron. In terms of slag metal reaction, soft jet promotes slag metal reaction. So, a soft jet, it promotes slag formation. a soft jet promotes slag formation. So, too long duration of soft blow, too long duration of soft blow is not good, because it may cause foaming of slag, and eventually sloping. I have taken two extremes, soft jet and hard jet. Hard jet, the depth of penetration will be large, depth of penetration is large, as just we have seen in the calculation. What does it mean? Now, the oxygen will be available deep into the bath, that means oxygen availability will be deep into the bath, What does it mean? That means now here the carbon reaction can be accelerated, because oxygen is abundantly available in the bath, so it will react with the carbon. But if phosphorus is to be removed, which is a slag metal reaction, then phosphorus removal will be impaired. So, I will write down here oxygen availability will be deep into the bath, on account of which carbon removal will be accelerated, but phosphorus removal will be impaired, simply because phosphorus removal is a slag metal reaction. Another important feature of this hard jet is that since carbon monoxide evolves deeper into the bath, so a better circulation in the bath as long as CO is being produced is there. So, that means CO evolution deep into the bath and which will create good agitation condition in the bath. Another important feature of this hard jet is that the droplets are produced. Now, when the droplets are produced and when these are entrained into slag, because of the high interfacial area, the reaction rate will be faster. So, in summarizing the effects of hard jet, the hard jet is preferred for carbon removal rate and inducing faster mechanism of refining reaction, whereas soft jet accelerates slag formation, and the soft and hard jet fits very well into the concepts of converter steel making, because steel making involves oxidation of impurities through slag formation. So, what we are having? By having a soft jet we can promote slag formation, by hard jet we can promote carbon oxidation, but if we want to carry out both reactions simultaneously, the slag metal reaction which is the phosphorus removal, the gas metal reaction which is the carbon removal, if we want to carry out both of them simultaneously, then we can create a condition from soft jet to progressively harder jet, and eventually we stop the blow at the hard jet. So, what I mean to say from here is that soft blow and progressively harder blow is the fundamental concepts of converter steel making, and almost all converter steel making in all industry, they have this particular concept of refining of steel, that is starting with the soft jet, making it progressively harder during the blow and eventually finishing the heat with somewhere between soft and hard blow. So, that is why the tape to tape time interval for all the converter capacities does not depend upon the size of the converter, because the refining schedule is attained by changing the lance distance in terms of soft and hard blow is independent of the capacity of the converter. So, let us take now the feed materials and practices. Feed materials and practices. Now, feed material say one requirement is low sulfur hot metal. Why low sulfur hot metal? Because in steel making sulfur removal is not possible. Then silicon control is also required. Silicon control is required, because larger is the amount of silicon, more SiO2 will form and more will be the volume of the slag. Then and also silicon retards the dephosphorization. Temperature is approximately 1250 to 1300 degrees Celsius. Then the feed material also we have steel scrap and ore. Steel scrap and ore. Say around 20 to 25% of hot metal scrap is charged. Now, one of the important requirement in case of scrap is the tramp element. The tramp elements like lead, antimony, tin, zinc, they are present in the scrap, and as such they will pass into the liquid metal, or they will create large amount of fumes, and they may pass to the exit gases if during steel making their boiling point is crossed. So, the control of tramp element is also an important issue while using scrap as a charge material. We use also fluxes, lime, magnesia sometimes depends. Then of course, gaseous oxygen, approximately 3 meter cube at 1 atmosphere and 273 Kelvin per minute per ton, and if you have capacities for example 220 tons, then we require 660 meter cube per minute of oxygen. So, that much amount of oxygen you should have. If you blow for 20 minutes, then you know what is the amount of oxygen you require. Then we also require deoxidizers. We also require deoxidizers to kill the steel. Now, practice. Typical heat, first of all lining inspection, lining is inspected. For any repair, if it requires to repair, then lining is repaired before starting the heat. Then charging of hot metal, then charging of hot metal and scrap, charging of hot metal and scrap, then lance is brought and oxygen begins to blow. In some practices the slag former, in some practices slag former and other additions they are done during the blow, it depends, I mean it varies from practice to practice, or prior to charging hot metal and scrap, prior to charging hot metal and scrap, or part during initial blow and rest thereafter. So, what is being said here? These are all the variations that vary from practice to practice. Some practice prefer to charge all in the beginning, some practice during the blow, some practice part during the blow and later during the period. It all varies, but does not matter. All that it requires, whatever amount is required to charge, it has to be charged during the refining operation. Then oxygen is blown, as I have said, oxygen is blown through a lance placed vertically about the bath. Now, here oxygen blow has to be controlled, and the oxygen blowing continues for 15 to 20 minutes, and during the blow the lance is raised or lowered such that the slag forming and oxidizing reactions remains within the control. So, what is important here? A lance schedule has to be developed. Now, the lance schedule development requires some cautions. Slag forming reaction should be there, carbon monoxide evolution should be continuously there. So, rising or lowering of the lance should go within the extreme of slag formation and CO evolution. That means, at no point lance distance should be such so that slag expels from the mouth of the converter. At the same time, lance distance should not be so low or should not be too low so that it allows only carbon reaction and no phosphorus reaction. That means, the control of lance distance right from start of the blow to the end of the blow is a very, very important exercise for any steel making operator who is working on the converter steel making. Now, in fact, these profiles are developed, they are fitted into the practice, and then the practice follow the same profile. So, at the end of the blowing, the samples are taken, analyzed for the specified chemistry, and then steel is being tapped. So, here are the questions for your self assessment on the oxidizing reactions. What is the principle of steel making? Write the chemical reactions. What are the essential requirements for removal of phosphorus from hot metal in steel making? Question number 3, mention the importance of CO reaction in steel making. 4th, 5th, 6th and 7th I had already discussed their answers. Please read the question and see that you are able to answer. Here are some references for reading on the oxidizing reaction, and these are the references for oxidizing reaction. Thank you.